So we covered the case where we get complex roots in the auxiliary or characteristic equation when solving this second order linear differential equation. And they look something of the form a plus ib, something like this. And, we kind of casually mention that if we get a solution that looks like this, or I guess specifically we had like an e to the at here, and there's an e to the at here, that, when we write out the final solution, we could kind of casually write it as like c1 e to the at times cosine of bt plus c2 e to the at times sine of bt. And I kind of hand waved and said that the I gets absorbed into this constant because I is itself a constant, even though it is an imaginary number, it's a complex number. It's going to get absorbed into this content or into this constant here, and we are interested in just what this final constant ends up being. So it doesn't matter that it disappears, we just care what we get at the very end. But I kind of wanted to elaborate a little bit more and give just a little bit of background, which was to prove that, if I have a solution of this form, and more generally, I'm going to rewrite this and just say that, let's suppose that we have some solution. It's going to be some function of t that looks like this. So we have a real part and an imaginary part. We'll call it v of t. Okay. And that if this is a solution to this differential equation, and this is a complex valued solution, that for us, the real part, which we can actually practically use in the real world, it is enough to just basically extract the real part and the imaginary part separately. So basically that if this is a solution, then, or a complex valued solution, then u of t and v of t are real valued solutions, that they will solve this differential equation. And the proof is relatively straightforward, right? Let's how do you check if anything is a solution? We can take this function and we just plug it into the differential equation. So we're going to get a times, and then what happens when we get the second derivative? We're going to get, u double prime plus I v double prime, and then plus b times u prime plus iv prime plus c times u plus iv, and supposedly, is equal to 0, right? That's what we want to know. We are hand waving a bit in the sense that this is not a complex calculus course, but we're going to say that since I is a constant, calculus rules work in the same way that we would expect them to work. And the idea here is all I'm going to do is I'm going to group everything together that has an imaginary part and group everything together that doesn't have an imaginary part. So I'm going to rewrite this as in the form, a u double prime plus b u prime plus c u, put that like in a parentheses, and then I'll have an I times a v double prime plus b v prime plus c v, and we're asking ourselves, does this thing equal 0? And so the question is, okay, so we plugged it in, we're checking, we're verifying this. But if we're a solution, okay, if this thing is supposed to equal 0, the only way that a complex number, right, a plus ib is ever going to equal 0 is if the real part is equal to 0 and the imaginary part is equal to 0. Both pieces have to be equal to 0. And so this implies, right, that, again, I've been putting question marks here, but there's no question mark because we know we're assuming that this thing is a solution. So we are assuming this is a solution, so we should get that it equals 0. And the only time that we're going to get 0 here is if both of these pieces are equal to 0. So this implies that this chunk has to equal 0, and it implies that this chunk has to equal 0. Well, if both of those things equal 0, then individually what this means, this means that my function u of t solves the ODE, right? Solves the ODE. And the second part also means that v of t has to solve the ODE, right? Solves the ODE, because the only way we're going to get 0 out of this, right, and that we know we're going to get 0 is that this thing has to equal 0. And if that equals 0, that means we plugged in v of t into this differential equation. We got out 0, which makes it a solution. So this is the reason why, if we ever had a differential equation and we got, say, r was equal to 2 plus or minus 3i out, and so we wrote out that our solution, y was equal to c1 e to the 2t times cosine of 3t, and then we could put in plus c2 I e to the 2t times sine of 3t, and this I showed up because of Euler's formula, right? Using e to the I theta was equal to cosine of theta plus I sine of theta. We get this I that shows up here, but it turns out that we get to ignore this I, and that the real part and the imaginary part end up being solutions. So we can kind of just it kind of just evaporates, and if you want to think about it like that, that this part is our usable bit of our solution as well. So just kind of an interesting little proof that exists here of kind of explaining a little bit more maybe what happens to that I and why we kind of ignore it and just use the real and imaginary part. So yeah, hopefully this was interesting. And yeah, check out my next one.